Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.1.2, the collection of encryption and decryption actions. Okay, so we're going to talk about what these actions are. And so we have a key over here, and that key is going to be sent to something it's going to do. And what is it going to do? It's going to send a message to something else, to an encrypted form of the message. So it's going to take a message to another message. It's going to be a function or map from M to M. So every action is going to be a function, okay? A function from M to M. Now, we'd like this encryption action to, or this function, we want to be able to describe it. Now, we could perhaps think of a random permutation on M and call that a function, but it would be so hard to describe what a random permutation would be as a function, especially if M is very large and a very large monstrosity of a set. That would be terrible. So we're going to simplify a little bit, but some things can be undercover yet still, because what we're going to do is maybe perhaps we can make M be a group, and our functions are going to be functions that preserve that group operation. Now, if we keep our group a secret and some other things secret, then actually this is quite nice. At least for us, we can have a quick way of knowing what our map is, what our function is, how to encrypt things and decrypt things, and be able to describe it very quickly and easily and figure out how to decrypt. And maybe no one else can, just because they don't know what group we're working in. But at least for us, we can quickly encrypt and decrypt things. Of course, there are ways of making the encryption process accessible even to the public, but they just can't decrypt. And we'll get there. Okay, so let's first think of our message as a small set, like a group, an additive group, where the group operation is commutative, like Z mod 5Z. Okay, and we're going to be looking at functions that go from Z mod 5Z to itself that preserve the operation of addition. Okay, so let's list out some possibilities. Multiplication preserves addition because it distributes over it. So we can think, all right, what if we multiply by 0, by 1, by 2, 3, 4? Let's let that be a collection of functions that preserve the operation of addition from Z mod 5Z to Z mod 5Z. So these could be our potential actions right here. Now, keep in mind, if we did like a 0 multiplication action, that's not really that great of an action if you want to encrypt and decrypt, because it's not reversible. You basically send everything to 0. But let's kind of look at the structure of the collection of these functions. So these functions themselves, let's throw them into a set and put some structure on that. For instance, we can do things with the functions. We can have operations between the functions. We can add functions together, like this, in this way, where we're just adding the outputs of the functions. And if we add the functions in that way, we're just adding outputs. Notice in this particular case that G plus H is equal to J. In fact, we end up getting a group. And actually, that group corresponds to Z mod 5Z under addition, where this is behaving like the 0 element. This is like the 1 element, the 2 element, the 3 element, the 4 element, as we add. And not only as we add things together do we get that structure, but actually when we multiply as well. Um, so for instance, but what does multiplication of these guys mean? It actually means composition when we compose these things together. So for instance, let's look at an example of that. Like we put one function into another one, like this one. We put h into j. What happens? Well, the function of h means multiplication by 2, function of j means multiplication by 3, and multiply them together, you get 1 times, which actually ends up being the identity function, where j and h must be inverses of each other, which makes sense because 2 and 3 are multiplicative inverses, mod 5. And if you compose k and j together, you end up getting h. So it really see this, but this composition is behaving a lot like is related to the multiplication here. So that's kind of a neat fact. In fact, so what is A? A is the set of these functions, you could say, or it's a set of the actions. So the actions are functions. So we're going to let A be the set of actions. It's a okay. We're going to let A be the set of actions that we actually chose, like that collection of functions. And notice that this is looking a lot like Z mod 5Z with addition and multiplication, where composition is behaving like multiplication, and adding functions will behave like the adding over here. Okay, so in general, if we want to generalize this idea, we take a commutative group with some operation. In our case, we were taking addition. We take action set, which is taken from maps or functions that preserve this operation between the message set and itself. And on this, so this is a set of functions here. That's what A is. And A, we can apply this up. Like if this is addition, we can add two functions together just by adding their outputs. And we can also compose the functions together. And we'd like the composition to be behaving a lot like multiplication. All right. So that's kind of the idea of our choice of A when we're kind of going to be thinking about these encryption decryption actions. Also, we want to make sure that that one of our actions is the identity action, which we had above here when we chose G to be just X to X right there. Okay. So, all right. So we kind of have this idea now. So so that's kind of our set of actions here. Now, how do we describe the set of actions? We can describe it in different ways. For instance, we could describe what's happening, which is like so our actions are like literally multiplication by 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. Well, we could represent that by integers. For instance, we could take maybe like 10, right? 10 is an integer. And what action does it represent? Well, 10 mod 5 is 0, so it would represent the 0 action. All right, what about 23? What action would that represent? Well, 23 is 3 mod 5, so it represents the 3 times action. So really every integer is like code for some action over here. So you could send it over here to the action. So here's this little example, like 2 as an integer can be sent over here to an action, multiplication by 2. Okay. So let's keep going here. All right, so we have this kind of a description here from integers and going to actions. Now, the function that assigns an action to an integer in our case, it actually preserves the operation of addition, and it turns multiplication into composition. Like, for instance, like 6 times 7 over here. As I put it into as I put it into mod 5 arithmetic over here. So modding out actually preserves things like multiplication and addition. So um, multiplication and addition. And here multiplication is like composition over here as well. So like everything transfers over very nicely. And we're going to call such a map or a function here that preserves the structure addition to addition. And here multiplication to composition. We're going to call this a cryptography map. And we even call it an outside multiplication, if you will, because things in here are acting over here basically as multiplication, because over here it's like you multiply things together, but here it'll be like composition. But even if you just take anything over here in Z, you can, and it's sent to a function over here. And the process of being sent to a function, we can actually notate. So like take K as an integer, and K lives outside of the message set. I mean, outside of Z mod 5Z, where all the action is taking place. Yet it acts on all the elements of that set because it is describing a function. And so, and the function action we call an outside multiplication. We can even notate it that way. So K times A bar. And it's defined like this. You throw the bar over the K, and then you put it together. And that's the action. That's where A is sent. For instance, right here, like where is 3 sent? It's sent to 3 times 2, which is 1 bar. Okay, so it describes a function here, and it's a function action. So this is like literally the function that K is sent to, and then you put A into it, and you get something out of it. It's called outside multiplication. So you have something outside your group, but you can still multiply by it, and it follows some basic rules in order to be a nice outside multiplication. Part of it is seen because these functions that these guys are sent to distribute over the group operation itself, and multiplication turns into composition. Those are some key elements of being a nice outside multiplication. Let's look at some examples and keep working through this. So for instance, we outside multiply by an integer 2 in Z to something in Z mod 5Z. Like this, we end up getting something like we get negative 2 bar. We can undo the action by multiplying by 3, because multiplication by 3 is like the inverse function of multiplying by 2, because, well, they're multiplicative inverses as well here. And composition is like multiplication. Okay, so we can undo what we did and end up where we started. Okay. But our outside multiplication or encryption decryption codes don't have to just live in Z. They could live somewhere else, like Z mod 10Z, for instance, if we're working with Z mod 5Z here as our group, and we're taking functions, function actions that preserve that group operation. For starters, we already have an outside multiplication by Z itself, by the integers going. So we have we have a map that sends quite literally this one that we notated right here. We have this map, that's our R. And we would like to know, well, do we get a map, an outside cryptography, outside multiplication map that goes from here to here? Can we outside multiply by elements of Z mod 10Z? So remember what we were doing. We were just, outside multiplication was, we just took something in here and we threw it under a bar and multiplied. So like here, we just take this and we throw it under a bar, and then we multiply. We put the bar over. So that's what's happening here. And is that same process well-defined going down this way? Throwing it under a bar. Well, there's a couple ways of looking at this. For one, Z mod 10Z is is a collection of chunks of in the integers. Um, so if you have like for instance, 10z plus 3, this is a coset um, of 10z, or it's equal to 3 bar. And notice that this is actually this is completely contained in 5z plus 3. So because so if we're 3 more than a multiple of 10, then we're 3 more than a multiple of 5. And this is true just kind of generally for any of these shifts of 10z, which means that for sure, if we were to take the collection of all the things here um, in this fiber, and then you would like to chunk them up, you notice that these guys definitely have a place to go under the bar. So popping 3 under the bar from here should be the same thing as taking a 3 in here and popping under the bar, because 3 under the bar is going to quite literally, so this bar is contained, so this fiber is contained in that one for sure. Like if something is 3 mod 10, it's also 3 mod 5. And so it should work very nicely to do that. That's kind of the idea. We can also, but how do we remember our identity to identity criterion? We can actually use that here as well. For instance, if we take the 0 of this, which is just multiples of 10, all right, and we put them back into, so this is just the quotient, like modding out by 10. So this is a skip pattern merge. If we put it back here, the pre-image of that's just 10z. So we take, so all multiples of 10, and you run it through this cryptography map, which just means throwing it under the, under. Well, what happens when we put 10 under the bar? Well, 10 is multiple 5. It's like putting 0 under the bar, which you end up getting the 0 function, multiplication by. So you end up getting the 0 function to multiply by if you had the 0 up here, which means we have a well-defined map that preserves addition. You could also look at something similar with multiplication with identities and notice that it's well-defined that way as well. Okay, so we have a nice well-defined map and it should work well. And part of the reason being is 10 is a multiple of 5 in that case, so throwing under the bar is just fine. And here's an example of that. So green means from mod 10 and red means here from mod 5. So we have 7 mod 10. You'd multiply it to something that's mod 5, because if we throw it into the bar, that's perfectly valid because the green fiber fits inside the red fiber of 7. And so it's completely contained in this chunk right here. So we can just simply replace this with that. So in our multiplication, we end up getting, we can do a little bar arithmetic, replace this with 7 bar and put bars back over and end up getting what we want. So this is a well-defined outside multiplication if we come from Z mod 10Z. Okay, so all right, so in general, we have a nice outside multiplication, as we were describing. If the functions themselves that are describing the outside multiplication distribute over the group operations, just like multiplication is distributing over addition. And the composition of the functions behaves like multiplication itself, and everything is well defined, just like we were describing being well defined, but we can really throw things under bars. Okay, so we can have an outside multiplication by the integers to a group like this. This is a Cartesian product of 2 different groups, Z mod 4Z and Z mod 6Z. We can use in your blue for the first guy and red for the second one. We outside multiply, so we have something outside of this group, like 2, which is in an integer, and it comes in, it just comes under the bars, and that's this is a well-defined action. Okay, let's look at example 6. Now it becomes when we want to outside multiply by something other than z, then there's more to check to make sure it's well defined. I mean, for z, we have our quotient, our um, regular skip pattern merge quotient type maps that we can use. But here, what if we want to outside multiply by z mod 12z? Notice, like in the case that 10 was a multiple of 5, well, 12 is a multiple of 4 and 6, so it should work. And you can think about it. The 0 that comes from here is like 12z, and 12z, if you throw it into here is like 0 for sure, and so you're going to get the 0 type action. So it's going to be a well-defined thing in that case. And since it works additively, it'll also work multiplicatively, because the additive identity is just 1 plus 12z. And so the 12z is going to go away. It definitely will preserve it all the way through. Okay, and we'll see an example of that as we go down later in a later example. So we'll postpone that for them. Okay, so right. So we have, since this is like a sub, we call it a subpartition. That's just because one of these chunks fits inside of one of those and one of those. So it's just, it fits inside. So we can define a nice outside multiplication, because this just becomes 9 bar, that just becomes 9 bar in that mod, and we can have a nice multiplication there. Okay, so let's look at another example. In this one, we are looking at our message set is a multiplicative group now with multiplication. So multiplication now is going to replace addition. And we're going to have an outside multiplication on this group, which actually will be exponentiation, because exponentiation actually distributes over multiplication like this. Raising something to a power is a well-defined idea, even in a mod. So so that's already well-defined, and it distributes over the group operation. And if you compose, like do one exponent then another, that's it, you actually multiply the exponents. So compositions like multiplication. So this exponentiation actually is a nice outside multiplication, just like here. So composition becomes multiplication. So let's look at this next example, example 8. Let's suppose that we want to take something in z mod 5z. Can we raise it to a power that's in another mod, like z mod 4z, for instance? I mean, definitely we can take something like, we can take something and raise it to a integer power. Can you raise it to a mod power? We know that when we raise things to an integer power, that's actually an outside multiplication from the last example. So really what we're trying to say is, can we outside multiply via exponentiation by the group z mod 4z when we look at z mod 5z cross? So this multiplicative group, can we do that? Does it make sense? Is it well defined? So being well defined really is the question here. You know, does that really hold? Is like the 0 of z mod 4z. So we're going to use the identity criterion. Does the 0 here via exponentiation, does that become the identity of this group, kind of like the of the actions? So the multiplicative identity, because now it's this is the main group operation of our message set, is multiplication instead of addition. And so the function where we multiply, so we want to get the function where we outside where we're multiplying by 1, which comes from outside multiplying by So the identity of the actions is actually just it's a function. Remember, A is a collection of functions. And the multiplicative identity in here on our, because we're using multiplication instead of addition, is the function that sends everything to 1. Instead of the function that sends everything to 0, it's the function that sends everything to 1. Okay, so that's like the identity here. And we want to know, does the 0 here, which is all multiples of 4, as we look back here, is that sent to the function that just sends everything to 1? Well, the function is given by an exponent. So that'd be like the exponent of 0. So kind of what we need is we need that that multiples of 4 should behave like an exponent of 0. And if they do, then the identity to identity criterion is holds, and we get something that's well defined. And we will get a well-defined outside multiplication here. Okay, so in general, we can actually see that this holds. Like just pick 3 and through the 0 through the 4th through the 8th, we always get 1 back. And this comes from the idea that there are 4 elements in that multiplicative group, Z mod 5Z cross. There are 4 things, 1, 2, 3, 4. And anytime you are in a group and you raise and you repeat a group operation on any element, but the number of times of the number of elements in the group, you always get back to the identity. And there's an exercise, and in the there's an exercise in the section on groups that goes over that. Also in section 4.3, there's a few exercises that work together to do that. Look at exercises 20 to 28. Also, there's a video in the discrete playlist that goes through that idea. Okay, so we're going to use, so essentially it does work. We end up getting something that's well defined, that preserves, that works with the okay, that sends the additive identity right here to the to the identity down here in the actions, the function that sends everything to 1 for the multiplicative identity. Now, what about the multiplication identity up here? Is it sent to the composition identity here, which is raising to the first power? And naturally, if something's 1 plus 4z right here, which represents a 1 bar over here, if you send it down this chute, which preserves addition, 4z just goes to 0, and you're just raising to the first power, so it should work. In fact, I think there's a little description of that right here. So it holds in both cases, for both types of operations. And so it's a well-defined multiplication. Really all we needed to show, even for the multiplicative part, we used this again. We just needed to see that the additive 0 really went to the identity down below with just the group, with respect to just the group operation, where you're sending everything to the identity element. So let's take a look at another example. So what about Z mod MZ cross? All right. Let's let n be equal to the size of that group. Then it should have an outside multiplication via exponentiation by Z mod NZ. Then is the size of the group. So basically what we're saying is the exponents of this multiplicative group live in mod n land. All right, mod n. That's where they live. So multiples of n behave like an exponent of 0. Okay. Now let's look at the next example. So we're going to let this bar refer to Z mod 7. And we know that powers of 3 repeat every 6 because there are 6 things in here. 6 numbers, 1, 2, 3, 4, 5, 6. that don't share any common factors with 7. And so you know the powers of this repeat every 6. So you could just kind of reduce this, think, okay, mod 6, and here in the exponent we have really mod 2. So really you can, it simplifies our calculations when we're working in mod 7 arithmetic when we're taking exponents, knowing where the exponents live. Okay, so let's look at another example. So an acceptable outside multiplication for z mod 7z cross via exponentiation comes from z mod 36z. That's because the exponents in 36z, okay, so are actually in 6z itself. All right, that means if you're a multiple of 36, you're a multiple of 6. And then, so it's going to be behaving like an exponent of 0. And so these guys will also behave like an exponent of 1. So this is just an example that we can have outside multiplication by any group, like z mod something. Well, this is an additive group, even though this is multiplicative. But by any group where what we're modding out by is a multiple of the number of elements of this multiplicative group. Thanks for watching.